In this section, we introduce ourselves to multivariable functions. Let's begin with a definition. Let's let D be a set of ordered pairs. Of the form x comma y, to each of which is assigned a unique number. Which we'll call f of x comma y. Then f is said to be a function of x and y. Where D is the domain of that function, and the collection of all x of all f of x comma y is called the range of the function. A bit of notation. We can say, okay, give me an ordered pair, x comma y. Now, to that ordered pair, we'll assign a number. We'll call it f of x comma y. That's a third value, which we'll often refer to as z. This is reminiscent of the algebraic f of x equals y, the thing you've seen all the way since algebra, where y is a function of x. Usually with a single variable function, what you have is, I have one variable, and to that variable, to that value, I'll assign another value, which we'll call y. So f of x is your y. Here we have your domain is made up of not just a single value, but rather pairs of values. And to each of these pairs of values, we assign a number, f of x comma y, which can also be referred to as z. In this case, we are going to use the familiar names of this is your dependent variable. It depends on whatever this is. Normally, you would have f of x equals y. Y would be your dependent variable and x would be your independent variable. However, here we have two independent variables. They do not depend on each other or anything else. They are just two random arbitrary numbers that happen to be paired together. But that pair gives us a dependent variable. Dependent and independent variables. One thing to note is that here we are defining a function with two variables. The argument is made up of two inputs. There's nothing that says we have to stop at 2. So note, similarly, we can define a function of 3 variables. Something like f of, instead of x or xy, we can say something like f of x, y, z. Here, just like we have y equals f of x or z equals f of x, y, here we would, well, we need something other than this, so we could say something like w. W is f of x comma y comma z. We would call this a function of 3 variables. And we go even higher. We could say a function of 4 variables or 5 or 6 or so forth. We could say f of x, y, z, w. That's equal to, oh, I'm running out of letters. Let's say u. And here you'd have a function of 4 variables. And so forth and so on. Note that eventually, as I mentioned, you kind of run out of letters. An alternate notation to this, we're not going to use this notation much here because for the most part we're going to stick with functions of 1 variable, 2 variables, or 3 variables. I believe there's, we don't have any need for anything higher than that for this course. However, in general, if you needed more variables, sticking to the convention of x and y and z very quickly sees you run out of letters. So another convention is to write things this way. You have f of x1, x2, x3. And that way you'll never run out. So that's a function of 3 variables. If you wanted a function of 4 variables, you would say f of x1, x2, x3, x4. And if you needed 5, 6, 7, you do whatever you need to. In this case, you could always use the convention that y equals this, or y equals that, or y equals the other, or any other letter you choose to use. So here we define a function, a multivariable function. Note that our domain is still all the stuff you could plug in. It's just that now instead of plugging in individual numbers, you plug in ordered pairs. Note that your range is still all of the outputs of the function, all of the possible results. Finally, note that this result is a single number. So this 2-variable function has an ordered pair as an input, but as an output, you end up with still just a regular number. So for example, consider the function f of x comma y is given by the square root of 16 minus 4x squared minus y squared. What we're going to do here is we're going to go ahead and consider different aspects of this function, and we're going to do so graphically, because oftentimes being able to summarize the features is simplest in a graph, and many times a graph will give you enough information to do other things, or at least gain intuition to do other things. So here we say f of x comma y equals this, and our question will be, we're going to go ahead and give the domain, the range, and describe the graph. All right, so let's consider this here. First of all, the domain is the set of all ordered pairs you could plug in. Notice our domain is not a number or even a set of numbers. It's a set of ordered pairs, x and y. All right. Well, even though you're plugging in pairs of numbers rather than single numbers, there's still numbers that you're plugging in here, which means they still have to follow all of the restrictions and conditions on regular arithmetic. You still cannot take the logarithm of negative numbers. You still cannot take the square root of negative numbers. You still cannot take division by 0. None of those things can be done, assuming you're dealing with real values. Oh, that is one more thing I should mention. In this course, we're only going to deal with functions, whether they be of a single variable, a single parameter, or multiple variables. We're only dealing with real value results, no complex or imaginary numbers here. So here, can you take the square root of a negative? Of course you can, but that would involve a complex or an imaginary number. Likewise with logarithms. Can you take the logarithm of a negative number? We can define the logarithm of a negative number, but as you see in Cal 2, it does require complex results, complex numbers. Right? So here, assuming we're using only real numbers and all of the restrictions and conditions therein, required therein, here we know that this must be greater than or equal to 0 underneath the radical. Otherwise, you're taking the radical of a negative, and that's not in the domain of our function. Right? It's not defined using real numbers. So our domain there we go. Our domain is, we need 16 minus 4x squared minus y squared. We need it to be greater than or equal to 0. Because if it's less than 0, then again, that's a complex number. Oh, sorry, this is a complex number, and our expression is undefined anyway for real numbers. Okay, well, normally we would say, okay, solve for x or solve for y. But in this case, we don't have the ability to solve for one variable because we have multiple variables. But we can still describe this graphically. Note that here, if I go ahead and subtract 16 over this way, I have minus 4x squared minus y squared is greater than or equal to negative 16. And then, if I go ahead and divide everything by negative 16, I end up with a positive x squared over 4 minus y squared, oh, that should be a plus now, right, since I'm dividing by a negative, plus y squared over 16 is greater than or equal to 1. And notice, if I ignore the greater than part, if I just say x squared over 4 plus y squared over 16 equals to 1, that's an ellipse. Oh, okay, so, and I multiplied by a negative number, which means that we reverse our inequality. So that greater than should now be a less than. Okay, so even though we cannot explicitly state, okay, our domain is x equals 1, x equals 1, y equals 2, x equals 2, y equals 3, and so forth and so on, what we can do is we can describe this graphically. Because after all, we know that x squared over 4 plus y squared over 16 equals to 1. That's an ellipse. And it's not particularly difficult to graph this ellipse either, because here, since it's centered at the origin, we can just plug in some zeros and see what happens. Here, if x is equal to 0, y must equal to positive or negative 4. Okay, so positive or negative 4. Here, if y is equal to 0, then x must equal to 2 or negative 2. 2 squared is 4. Negative 2 squared is also 4. Okay, so then x value, when y is 0, x must be 2 or minus 2. So this is the ellipse given by x squared over 4 plus y squared over 16 equals to 1. Oh, but we don't want equals. We want less than or equals. Okay, well, that must mean that I want either everything on the inside of this ellipse or everything on the outside. Okay, well, plug in a test point. Let's use a test point. I like 0, 0, because clearly 0, 0 is not on our ellipse, it's inside. If 0, 0 works as a test point, if it solves this inequality, then yes, we want the things inside. If it doesn't work, well then clearly we don't want things inside the ellipse, we must want things on the outside. Okay, so let's go ahead and plug in 0, 0. This gives us 0 squared over 4 plus 0 squared over 16 is less than or equal to 1, which clearly it is. 0 plus 0 is less than 1. So that means that, yes, my test point is a valid solution to this inequality, and so everything inside of this ellipse is a valid solution to my inequality. So my domain is, I want all the points which make this greater than or equal to 0, which we find as being all the points on the edge of or inside of this ellipse. So there's our domain. We can give it as a graph, and that's a fairly simple way to give it, a fairly efficient way to give it. However, if we were not able to give it as a graph, if we wanted it as a collection of ordered pairs, that's not really possible. However, we can write this instead. So either of these would be fine. If you want it graphically, of course you can graph it. If you want it algebraically, you would state it as, oh, my domain is the solutions to all of these things. Now, considering the range, again, we're restricted to regular arithmetic, because even though our domain is a collection of points rather than individual numbers, they're collections of ordered pairs, those ordered pairs still have me plugging in numbers here. Okay, so I'm taking the square root of 16 minus stuff. Oh, well, there's a maximum, right? 16. If I'm subtracting things from 16, then the biggest this will ever be is 16. Since 4x squared plus y squared must be greater than or equal to 0, right? Because when you square something, it's positive. And if you add positive things, it must be positive. Then 16 minus 4x squared plus y squared, right? That's the same as that one when you distribute your negative. That must be less than or equal to 16. All right, because you're subtracting either 0 or you're subtracting more than 0, greater than or equal to. So if you're subtracting 0, you're left at 16. If you're subtracting more than 0, well, then it's less than 16. Okay, but then this also has a minimum. You say, no, it doesn't. I could keep subtracting forever. Well, sure, but that's not going to make your square root very happy, is it? When you take the square root, what's the smallest thing you can take the square root of? Oh, that would be 0. So, and since the smallest radicand can be 0, if you go below 0, that's the square root of a negative, which again is not a real number, then that means that our f of xy has to be less than or equal to the square root of 16, greater than or equal to the square root of 0. Right? The stuff underneath the radical has to be less than 16. So the function must be less than the square root of 16. The smallest thing inside the radical can be 0. So the function must be greater than or equal to the square root of that 0. Or in other words, f of x comma y must be between 0 and 4. And there we go. So that must be our range. Notice this value is not a set of ordered pairs. It's just a number. F of x comma y is just a single number. And that single number is somewhere between 0 and 4. So that would be our range. From 0 up to 4. Finally, we want to talk about the graph of this. Okay. Well, remember, this is z. Your f of xy, you can think of that as being z. So this is really z equals this square root. Okay, so f of x comma y equals square root of 16 minus 4x squared minus y squared. That's the same as saying, well, that's z equals square root of 16 minus 4x squared minus y squared. But that looks very, very familiar. After all, if I square both sides, I end up with something squared, and something squared. We saw that in the previous chapter. Let's actually go ahead and do that. Let's go ahead and square both sides. That's going to give us z squared equals 16 minus 4x squared minus y squared. And now we can go ahead and add both of these over to this side to give us x squared plus 4x squared plus y squared plus z squared equals 16. But notice that's an elliptoid. Right? If this was just x squared plus y squared plus z squared, that would be a sphere. But since you have a constant here, it's going to stretch things out just a little bit so that you end up with a elongated sphere, an elliptoid. Here you may wish to write this in this form, where we have this as a constant 1. So let's divide everything by 16, which would give us x squared over 4 plus y squared over 16 plus z squared over 16 equals to 1. Obviously, both of these are the same, but this is usually the way we see elliptoids because, of course, if you take the traces, those are individual ellipses. So let's take a look at the graph of this. We can take some traces here. We know the xy trace. Well, that's when z is equal to 0. Okay, so then that's going to give us an ellipse. X squared over 4 plus y squared over 16 is equal to 1. Notice here, if, well, you're on the xy plane, we want y equal to 0. Well, that'll give us x is equal to 2 or minus 2. So 2 or minus 2. And if we want x equals to 0, y must equal to 4 or minus 4. 4 or minus 4. Oh, sure. That's on the xy plane, right? That was our domain. That was our domain. You want to go 2 units in either direction along the x-axis, or 4 units along either direction along your y-axis. Oh, sure. This is just a 3-dimensional representation of the entire graph, but this down here on the xy plane, that was just our domain. Okay, so we would have an ellipse that looks like that. Okay. If we take the xz trace, well then y would equal to 0. And you'd have x squared over 4 plus z squared over 16 equals to 1. And that's exactly the same thing, except instead of going 4 units in the y direction, here that would be 4 units in the z direction. So 2 units in the x direction, and then you'd want to go 4 units in the z direction. So up 4 down, and then down 4 this way. And finally, if you were going to take the yz trace, notice that that one's actually a circle, because here those are both the same. So if you take the yz trace, you'd have y squared over 16 plus z squared over 16 equals to 1. Or if you prefer, you may write this in the way you usually write a circle. Let's go ahead and multiply both sides by 16, giving us y squared plus z squared equals 16. Or in other words, it's a circle of radius 4. Okay, so circle of radius 4 on the on the yz plane. Okay. So it looks like we have that elliptoid, where you have a circle in this direction and you have ellipses in every other direction. However, that's not quite right. You say, well, obviously that looks crooked. Well, my limited art skills notwithstanding, that's still not right, because we're ignoring something that we stated a moment ago. The domain is all the stuff inside of this. Yeah, that's fine. We got that. Look, it doesn't leave there. It's clearly inside of this region. Okay, but don't forget your range. Your range is from 0 to 4. Notice there's no negative values here. But remember, your range is all the values of f of x, y. In other words, it's all the values of z. So here z has to be from 0 to 4. Oh. So nothing down here. So because since z is bound between 0 and 4, we have only the upper half of the elliptoid. So our graph would be everything from the xy plane going up. And here, sure enough, it only goes up to 4 anyway, right? The maximum height of z was 4. So here our graph would only consist of the upper half of this ellipsoid. And there we go. I may as well erase this part down here. Note that this visual gives us a nice representation of our graph in 3 dimensions. I give you a point. Let's say I give you the point, let's see, this was 2, this was 4, negative 4, and negative 2 back here. Let's say I give you the point 1, 2. Okay, 1, 2. All right, where's 1, 2? Well, it's over here. I'd go 1 in the x direction and 2 in the y direction. So right about there. Is that in the domain? Yes, it's clearly inside of there. Okay. Now let's say I apply the function. What is f of 1, 2? Well, remember, that's your z. So what this is saying is find on here your x comma y, and now find what z value is appropriate to that x and y. Okay, we'll follow that up, and where it hits that dome, where it hits that bubble shape, oh, that's your z. So what this is saying is find where on this flat plane you are, and then the function can be applied and tell you how far up you are. Z equals, here it's hard to see, right? What I did here was I said, okay, this height is z. That's the letter Z. It's just kind of squeezed in there. This height from the point straight up until you hit the dome, that's Z. And so here is your illustration, minus the. Now, oftentimes, a graph can be very useful in, well, in many things. At the very least, it's useful in helping us gain some intuition of, okay, what should I do? Well, if it looks a certain way, it may fall into a certain pattern. However, graphs will sometimes be difficult to come by. It's going to be difficult to graph something, especially in 3D. So while this would be very useful, we have a bit of a compromise. We have a way of getting a visual that doesn't require a full three-dimensional sketch. So note, while a sketch in space can be useful, we can often gain good information from level curves. I mentioned this once before when we talked about the traces of a graph. When you have a trace, you take one of your variables and set it equal to 0. The xy trace is when you set z equal to 0. However, you don't have to set things to 0. Those are called level curves. So we can describe those as, we can get good information from level curves. Curves along which f of x comma y is a constant. Not necessarily 0, just a constant. So let's take a look at an example of this. Here, I'm going to give one that's very similar to the one we just graphed. That way we can compare them. It won't be exactly the same, but similar. Here, we're going to go and sketch the level curves at c equal to 0, 1, 2, and 3 of the function f of x comma y equals the square root of 9 minus x squared minus y squared. All right. When we say we want level curves at c equals this, this, or this, what we mean is instead of taking z and setting it equal to 0, so when we talk about our level curves, unless there's a reason we're doing otherwise, what we're doing is we're setting z equal to something. We're looking at the xy trace and things that are parallel to the xy trace. So here, if this is our z, what we want to do is we want to set z equal to each of these values and find those curves. All right? So if c is equal to 0, then that means that this square root is equal to 0. Okay. Well, we could square both sides. So that would give us 0 equals 9 minus x squared minus y squared. Squaring 0 still stays 0. Squaring this gets rid of the square root. And then here we can take these and move them over. And this would give us x squared plus y squared equals to 9. Oh, that's a circle of radius 9. Okay. Let's take c equal to 1 and see what happens there. That should be 1 equals square root of 9 minus x squared minus y squared. I can now square both sides. Well, squaring 1 still gives me 1 is equal to 9 minus x squared minus y squared. And here I could subtract the 1 over this way and add the variables over the other way, giving me x squared plus y squared is equal to 8. Okay. All right. Let's say c is equal to 2. Well, that would give me 2 is equal to the square root of 9 minus x squared minus y squared. That would give me, well, I could square both sides. Squaring 2 gives me a 4 is equal to 9 minus x squared minus y squared. I could subtract the 9 and add the variables over this way, giving me x squared plus y squared equals 5. And then I'm going to say c equals to 3. So 3 is equal to, notice every time our level curve at c equals to a number, that means z is being replaced by that value, is equal to 9 minus x squared minus y squared. You'll also notice that each time we simplify, it looks like we're getting a circle each time. That's going to be meaningful in a moment. Here we're going to have x squared plus y squared equals to, if I subtract the 9 over, I get 0. So these are all circles, except this one is a point at the origin. The only way to add x squared and y squared to get 0 is if both x and y are equal to 0. Okay, so those are the values that I plugged in, and these are the results that I got. What does that mean? Well, let's look at a graph. Each of these is a circle, which I guess technically is a circle, but really it's just a point. You could call that the circle of radius 0 if you were very, very pedantic about it, which of course, being in a math class, maybe it's a good idea that we're pedantic about it. Here, that's a circle of radius 3 centered at the origin. Okay, so from the origin I'd go 3 units in every direction and connect my dots. Here you may notice that this is more of an ellipse than it is a circle, and that's got more to do with me drawing this freehand. It is intended to be a circle. Okay. All right, now x squared plus y squared is equal to 8. All right, well that's still a circle, but now instead of having square root of 9 as the radius, I'd have the square root of 8. Square root of 8 is 2 point something. Here, let's go ahead and actually take it. There you go, 2.8-ish. So not quite 3. Okay, so right about here. All right, so it's a circle that's slightly smaller than the previous one. Now it's still a circle. Just like that. Okay, x squared plus y squared is equal to 5. Okay, well that's also a circle, but now the radius will have, that it'll have is the square root of 5, which is about 2.2. So just past the number 2. Something like that. And then when c is equal to 3, it looks like I just have the point at the origin. Now you might say, well, what are these c's? I mean, here you're graphing this on the xy plane. Where are your c's? Here, I can label this as having c equal to 0. This is having c equal to 1. This is having c equal to 2. And this as being c equals to 3. Here's what this means. Let's say you graphed every point of this surface in space. Let's say you actually took the time to do the full graph rather than just these level curves. All right, what are all the points where your height, or your z value, is equal to 0? Oh, it's all of these. It forms this circle. All right, now let's say I wanted to go up a little bit. Okay, well then, let's say I go up just one step along the z-axis. Oh, well, it looks like all the points that do that are a circle inside of that bigger circle. And the higher I get, the smaller my circle is, until eventually I get to c equal to 3 when I'm down to a single point. Oh, what that looks like to me is, if I'm doing this in 3 space, I have, well, it looks like my domain is a circle of radius 3 and everything inside of that. So 3, 3, 3, and 3. And then every time I take a step higher, I get a smaller circle. So something like this, and then something like this. And eventually I get to a point. Oh, guess what? That's exactly what we had before, isn't it? What the level curves do is they tell you, give me a height. Oh, I want to be on the ground, the XY plane. Okay, well then here are all the points that keep you at that height. Okay, actually I want to be 1 step up above the XY plane. Okay, here are all the points that give you that height. Slightly smaller circle. Oh, I want to be 2 steps above. Okay, well here are all the points that keep you 2 steps above. Oh, I want to be 3 steps, 4 steps above. Okay, well, it looks like the only place where I'm 4 steps above the origin is going to be right there at that point. Oh, so I'm down to a single point. So by seeing this as a set of concentric circles, as C gets bigger, you get higher, even though you didn't take the time to graph the full image, it still suggests that that's what's going on. The higher you get, the smaller your circle is, so higher gives you smaller circles. Oh, you probably end up with some kind of a dome shape, which is exactly what we would have here. This would be the upper half of a sphere of radius 3. Okay, go ahead and give this a try. So you're going to sketch the level curves. Example. At C equals to 0, plus and minus 1/2, plus and minus 1, plus and minus 3/2, and plus or minus 2. All right, so you're going to have several level curves. 1, 2, 3, 4, 8, 9 level curves. Sketch those 9 level curves for the function f of xy equals the natural log of x minus y. So remember, you're going to take those, you're going to plug them in for z, in other words, right here. Do your best to simplify this so that you can graph it. And then once you've graphed them, you'll get your level curves. And try to figure out what that suggests in space. That's not really part of the question here. You just have to sketch the level curves. But as you do that, try to consider what that graph would look like in space. All right, go ahead and pause the video, give yourself the time you need, and then once you're done, we can go through them together. All right, so C equals to 0. That's going to be 0 equals natural log of x minus y. Now, natural log is kind of an unpleasant thing there, isn't it? So let me exponentiate to get rid of the natural log. Here, e to the 0 is just the number 1, which is great. I like constants. Equals to, here, e to the natural log of x minus y is just x minus y. Oh, that's linear. Here I can even write this as, let me add my y and subtract my 1. I can even write this as y equals x minus 1. All right, there we go. That's one of my level curves. This turns out to be just a straight line. Okay, let's try C equals to 1/2. Well, that would be 1/2 equals the natural log of x minus y. Oh, but let me do the same thing. Let me exponentiate with the base of e. Now, unfortunately, here that's not so nice, but that's okay. At the very least, it's getting rid of a logarithm. Here, that's still a constant, albeit a less nice constant. That's e to the 1/2 equals x minus y. Oh, but that's linear too. Since that's a constant, this is a linear function of y as a function of x. So here I can add my y, subtract my constant, and I get y equals x minus e to the 1/2. I could do c equals to 1. I'll just do the positive ones for now. Here, that would give me, well, let's see, that's 1 equals natural log of x minus y. Oh, but I could exponentiate. And at this point, you see a pattern, yes? Here, that's going to give me e to the first power. And that's just going to give me x minus y. So that'll give me, I can add my y, subtract my e. That'll give me y equals x minus e to the first. And notice my level curves are basically just y equals x minus e to that number. E to the 0, e to the 1/2, e to the 1. Just to confirm this, I'll do one more. Let's do 3/2. C equals 3/2. If I'm correct, my answer should be x minus e to the 3/2 by the time I'm done. So let's give that a try. 3/2 equals the natural log of x minus y. If I exponentiate with a base of e, got a little overzealous there, that would give me e to the 3/2 equals x minus y. Add my y, subtract my constant, and sure enough, that is the pattern. X minus e to the 3/2. So it looks like my level curves, I can skip the next, I can skip going through the arithmetic. I know how it's going to work out. I can say c equals 2. That's going to give me y equals x minus e to the 2. I can say c equals 2. Now, I need all the negatives, right? So that's going to be negative 1/2. That would give me y equals x minus e to the negative 1/2. C equals to negative 1. That would give me y equals x minus e to the minus 1. C equals negative 3/2. That's going to give me y equals x minus e to the negative 3/2. And finally, negative 2. If c is equal to negative 2, I end up with a level curve that is y equals x minus e to the minus 2. Okay, so now we are going to go ahead and graph these. Note that they are all linear equations. In fact, they're all going to be linear equations with slope of 1. Really, the only difference between any of these is the y-intercept, right? Y equals mx plus b. They're all just going to have different values of b. All right, so let's take a look. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 10. All right. So let's go ahead and graph these. Y equals x minus 1. Okay, well, my intercept must be minus 1, and it's got a slope of 1. Okay, so just like this. And I'll even go ahead and label that. That's what happened when c is equal to 0. Okay, now let my value of c grow. All right, let's see here. E to the 1/2. Well, let's see here. E to the 1/2, that's about 1.6. Okay, so that's y equals x minus 1.6. So it's still going to be parallel to this line. In fact, these are all going to be parallel. They all have the same slope. The only difference is what this value is here. So it's going to be about 1.6, so right about there. And again, it's got a slope of 1. So if that's 1.6, that'll be 1.6 as well. All right, so here we have c equals to 1/2. Let's try c equals to 1. Okay, well, that's e to the first power. Oh, well, that's about 2.7. So that'll be y equals x minus 2.7. So I'm going to go down almost all the way to negative 3. And then I got a slope of 1. So my level curve will look something like this. So here I get c equals to 1. Let's do 3/2. I can take 3/2, that's 1.5. So e to the 1.5, that's about 4.5. So this one will be y equals x minus 4.5. Okay, so down 1, 2, 3, 4.5, give or take. And I got a slope of 1, so that'll also go this way, 1, 2, 3, 4.5. So here I have c equals 3 halves, and then c equal to 2. Well, let's see, e to the second power, that'll give me about 7.4. Okay, so that one would be y equals x minus 7.4. So down 1, 2, 3, 4, 5, 6, 7.5. And 1, 2, 3, 4, 5, 6, 7.5, give or take. Notice that these are all straight lines. Notice that they are all parallel to each other. And notice that they're getting further apart. Here, these were really close together. And this one was slightly further out, and then this one. And then here, you'll notice that this one's actually really pretty far away from the previous one. C equal to 2. Okay? All right, now let's grab some of the negative ones. Let's try c equals negative 1/2. As you were moving away from c, you started coming, your line started coming this way, and it started spreading out. Let's see what happens as we go in the other direction from 0. Let's try negative 1/2. Okay, well, we saw that y equals x minus e to the minus 1/2. All right, so let's see what e to the minus 1/2 is. That's about 0.6. Okay, so this one was at negative 1, so 0.6 is slightly higher. It's closer to the origin, but not by very much. Okay, so these two are really, really close together, and that one's going to be c equals to minus 1/2. Let's try minus 1. That's what happens with c equal to minus 1. All right, so if I take e to the minus 1, that's about 0.4. Well, the last one was 0.6, so the next one is also closer to the origin, but still really close in there. Okay, well, it's still got a slope of 1, so it's going to be parallel to these, but now this one is even closer than the previous one, like this. So here I'd have c equals to negative 1, and I'm going to do the next one. What is e to the negative 3 halves? Okay, well, negative 3 halves, negative 1.5. If I take e to that power, I get about 0.2, which is really, really close. I'm taking x minus 0.2. So it's really close to the origin, but still not at the origin. I'm below the origin. It's minus that number. Oh, sorry, minus that number. So that's even closer together. And that would be c equals to negative 3 halves. And finally, if I have negative 2, if I take e to the minus 2, that's going to give me about 0.1. And that's, okay, x minus 0.1, which is even closer to the origin, but it's still just slightly below. So notice that as you move this way, your lines all get further and further apart. As you move this way, they get closer and closer together, but they're always parallel. No exception. They all have a line with a slope of 1. At this point, I'm not even trying to graph. They're so close together, there's no way I can pull that off. So here I'm just saying, okay, very close. All right, so this is my system of level curves. What is this? So first of all, what you have to realize is this is a top-down view. You are looking at, that's my x-axis, that's my y-axis. You might say, where's my z-axis? You are the z-axis. Currently, you are floating above. You are at z equals to 100 or something. You're way up above here. You're floating up in space. And you're looking down on the graph of this object. So what you're noticing is that as you move closer to the origin, your graph, it's got a negative z value. In other words, it's below the ground. So right here, this line where c is equal to 0, that's on the ground. All of these, they're actually further into the ground. They're underground. However, as c is positive, they're coming closer to you. But notice, as they get closer to you, they're bending around this way. What you have is, you have a sheet that is folded this way. Here, it's really, really steep. And in fact, it's it looks like it has an asymptote there. It's getting really, really close to the origin, but it's never quite touching it. So what you have there is, here I'm drawing some lines that are equidistant or close enough, if I'm doing them freehand. What you have is, here's a sheet that's been folded this way. Notice that here, these are all equidistant from each other, or at least close enough. But if I bend it this way, it looks like these are further apart, and it looks like these are really close together. It looks like these are very close together, and as this gets closer and closer to being flatter, they look like they're further apart. That's what's going on here. What we have is a sheet that it has an asymptote as you head toward the origin here. It never quite touches the origin. It's always just below it. And then as you come up away from the axis, what's happened is this sheet has been bent going in this direction. All that from just a few straight lines. Finally, for this section, let's go ahead and look at an extension of this. Because notice that I have a surface in space. In the previous chapter, we defined this as a surface, right? Z equals a function of x and y. However, here I did a completely two-dimensional drawing of it. Now, I'm asking you to try to imagine it in space. But here, this drawing that I've made is completely on the plane. It's just a bunch of lines on the xy plane. So it is possible, by using level curves, to draw something that belongs in space and containing it on the plane. The natural extension of this is, well, what if I had a fourth dimensional object? Length, width, height, and some other spatial dimension, which frankly I'm not quite sure how to name. Well, if I have something that's three-dimensional, and I can graph it on 2 dimensions, if I had something that was fourth dimensional, I could use the same principle to graph it in 3 dimensions. These are called level surfaces. So note, level surfaces are the extension yeah, that looks better. I spelled it with a T originally. That looks better. Extension of level curves to a 3-variable function. So after all, level curves are used for a 2-variable function. Level surfaces would be the extension of that to a 3-variable function. As a very simple example, relatively speaking, let's sketch the level surfaces. Sketch the level surfaces of f of x comma y comma z equals x squared plus 1/4 y plus squared minus z at c equal to 1 and c equal to 2. Notice what I'm asking you to do. X, y, and z, those are my independent variables, which means my dependent variable must be a 4th variable. This is an object in 4 dimensions. That's not possible for us to draw. Anecdotally, it was said that Professor Einstein could visualize things in 4 dimensions. Whether or not he could, I guess we'll never really know. We don't know what was in his head. But, well, for those of us who are not Einstein, and, well, I think that is all of us, fortunately, we don't need to. We don't need to visualize things in 4 dimensions. Because even though this is a 4th dimensional object, we can consider its level surfaces, which will exist 1 dimension lower. Just like the object here is 3-dimensional, but its level surfaces exist in 2 dimensions, this 4th dimensional object will have level surfaces that exist in 3 dimensions. There will be a few occasions in later parts of the semester and later parts of this course where we are going to consider three-dimensional objects as level surfaces of a fourth-dimensional thing, a fourth-dimensional surface. And oddly enough, that will make some things more convenient. You would think, oh, higher dimensions would make things harder, but when done at the appropriate time, using three-dimensional objects as level surfaces of fourth-dimensional objects actually does simplify some things, as we'll see in later parts of our semester. But for now, we can go ahead and sketch these level curves because they're going to work the same way as the previous level curves did. These are going to replace our dependent variable. So here, when c is equal to 1, that's going to be 1 equals all of this stuff. 1 equals x squared plus 1/4 y squared minus z. And when c is equal to 2, here, let me go ahead and write this. Let me put my z over this way. So that's z plus 1 equals x squared plus 1/4 y squared. Over here, this would be 2 equals x squared plus 1/4 y squared minus z. And here, if I move my z over this way, I get z plus 2 equals x squared plus 1/4 y squared. Actually, what I would like to do, let me go ahead and move this over this way as well. So instead of having z plus 1, let me go ahead and put the minus 1 on this side instead. And same thing here. Instead of saying z plus 2, let me say minus 2. Yes, these are equivalent, right? You can always subtract 2 from both sides. However, this will make the next part of the explanation all that a bit clearer, I hope. If you consider the level surfaces of this is quite clearly a paraboloid. Because after all, if you take your level surface where x is equal to 0, if you take your trace where x is equal to 0, that's z equals 1/4 y squared minus 1. That's a parabola. And in fact, so is that one. That's a parabola. If I make y equal to 0, well then that's a parabola. And notice that the only difference between this parabola and this parabola is that this one is one step lower than that one. And same thing here. The only difference between this first parabola and the second one is that this one is one step lower than that one. So if I graph these things, here, that would be the simplest thing to graph. If I set y equal to 0, here I have z equals x squared plus 1. Okay, well that's just the standard parabola shifted down 1 from the origin. Okay, so that would be something like this. That would be one step below the origin. Oh, but if I did that for this other level surface, c equals to 2, well, that would be the exact same graph. Oh, except that would be 2 steps below the origin. Something like this. Okay, if I did this level curve, like that, if I did this trace, rather, where x is equal to 0, well, then I'd have 1/4 y squared. Okay, well, that's a parabola facing up, right? That's a positive coefficient. Oh, but since it's not z equals y squared, but z equals 1/4 y squared, the whole thing gets a little shorter and wider, a little more opened up. Okay, so you end up with a parabola that's a little wider and more opened up. And same thing over here, a parabola that's a little wider and a little more opened up. But in both cases, this one is going to be 1 step below the origin, and this one will be 2 steps below the origin. So when I graph these all together, one of them is a parabola, a paraboloid. That's 1 step below the xy plane. And this other one is a paraboloid that is 2 steps below the xy plane. This and this are just different level curves of a fourth dimensional object. Can you visualize that? If you can, well, then you're far more capable than I am. As I mentioned, it is said that Professor Einstein could visualize those things, but, well, I'm nowhere near that ability. I don't have anywhere near that ability. But, again, I don't have to. These are the level surfaces from which I can gain some intuition and some strategies for later parts of our course. All right? But for now, that is it. If anybody has any, oh, and I guess I should label these, right? That one's, this is the level surface where C is equal to 1, and this is the level surface where C is equal to 2. So that is it for our topic and our section. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.